English and AEC. Parametric architecture. 1. Glossary of computational terminology and parametric design.
Parametric design. Parametric design. Computational design. Computational design. Computational architecture. Computational architecture. Computer science. Computer science. Arithmetic architecture. Arithmetic architecture. Geometry. Geometry. Minimal surface. Minimal surface. NURBS curves. NURBS curves. NURBS surfaces. NURBS surfaces.
Supply. Supply. Topology. Topology. Highly customizable convoluted geometry. Highly customizable convoluted geometry.
When you examine any parametric structure, you will discover that it does not adhere to any symmetry notions and defies standard geometry. When you examine any parametric structure, you will discover that it does not adhere to any symmetry notions and defies standard geometry. An universal set of building rules. To guide the design of organic structures, from simple carbon compounds to complex cells and tissues. An universal set of building rules. To guide the design of organic structures, from simple carbon compounds to complex cells and tissues. Mathematical algorithms. Mathematical algorithms. Cellular automata. Cellular automata. Fractals. Fractals. L-systems. L-systems. Voronoi. Voronoi. Algorithm. Algorithm. Argument. Argument. Associative programming. Associative programming. Boolean algebra. Boolean algebra. Natural systems. Natural systems. Biomimetics. Biomimetics. Bottom up. Bottom up. Complex adaptive systems. Complex adaptive systems. Darwinian evolution. Darwinian evolution. Evo-devo. Evo-devo. Flocking. Flocking. Emergence. Emergence. Morphodynamic. Morphodynamic. Morphogenity. Morphogenity. Nonlinear. Nonlinear. Top-down. Top-down. Building energy consumption and daylighting simulation. Building energy consumption and daylighting simulation. A common thread connecting the natural design of the world with human-designed buildings. A common thread connecting the natural design of the world with human-designed buildings. Computation. Computation. Brute force. Brute force. Dimensionality reduction. Dimensionality reduction. Fitness. Fitness. Fuzzy logic. Fuzzy logic. Genetic algorithm. Genetic algorithm. Solution space. Solution space. Pareto optimality. Pareto optimality. If-then rules. If-then rules. Recursion. Recursion. A superficial understanding of computational design and further undermines its adoption. A superficial understanding of computational design and further undermines its adoption. It is portrayed as a tool rather than as a philosophy of design. It is portrayed as a tool rather than as a philosophy of design. Process. Process. Algorithmic. Algorithmic. Algorithmically. Algorithmically. Data analysis. Data analysis. Various performance data. Various performance data. Generative design. Generative design. Parametricism. Parametricism. Parametric modeling. Parametric modeling.
Parameters. Parameters.
Parametric rules can qualify an architectural element and create relationships between different elements of the design. Parametric rules can qualify an architectural element and create relationships between different elements of the design. Parametric BIM. Parametric BIM. Generate, extract, and manipulate data. Generate, extract, and manipulate data. Analyses and embedded. Analyses and embedded. Parametric equations. Parametric equations. Partial differential equations. Partial differential equations. The computer software parametricism. The computer software parametricism. Adaptive, parametric malleability. Adaptive, parametric malleability. 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 Mathematical. Mathematical. Solve. Solve. The logic and theory behind the process. The logic and theory behind the process. Some parametric modeling software, Rhino, Grasshopper, Revit, belong BIM. Dynamo, Vectorworks, belong CAD. Some parametric modeling software, Rhino, Grasshopper, Revit, belong BIM. Dynamo, Vectorworks, belong CAD. Fabrication. Fabrication. Digital fabrication. Digital fabrication. Mass customization. Mass customization. Mass production. Mass production. Material feedback. Material feedback. Robotic fabrication. Robotic fabrication.
2. Cybertecture of Metaverse.
Metaverse. Metaverse. Most congenial. Most congenial. Cybertechnology. Cybertechnology. Cybertecture. Cybertecture. Cyberurban city. Cyberurban city. Virtual city. Virtual city. Virtual environments. Virtual environments. Virtual reality realm. Virtual reality realm. Integrated and seamless cybertecture. Integrated and seamless cybertecture. Intelligent control systems. Intelligent control systems. Libertarian micronation. Libertarian micronation. Freestanding. Freestanding. Networking and collaboration. Networking and collaboration. Fullest exploitation. Fullest exploitation. Digital replica. Digital replica. A cloud-based platform. A cloud-based platform. Photorealistic rendering. Photorealistic rendering. Innate and learned. Innate and learned. Intuitive cognitive capacities. Intuitive cognitive capacities. Social atmospheres and situations. Social atmospheres and situations. The micronation's eventual physical presence. The micronation's eventual physical presence. Realism. Realism. The physical micronation. The physical micronation. Physical realization. Physical realization. Lossy compression. Lossy compression. The crypto ecosystem. The crypto ecosystem. Crypto incubator. Crypto incubator. Cryptocurrency. Cryptocurrency.
3. Zaha Hadid's architecture.
Daring and unconventional. Daring and unconventional. Significant break though. Significant break though. A new dynamic way. A new dynamic way. Geometric abstract art. Geometric abstract art. Radical and experimental design. Radical and experimental design. Daring intensely creative. Daring intensely creative. Signature style. Signature style. Broaden the horizons. Broaden the horizons. Inspired new architectural thinking and process. Inspired new architectural thinking and process. Abstraction. Abstraction. Fragmentation. Fragmentation. Weightlessness. Weightlessness. Zero gravity. Zero gravity. Can float. Can float. Fluidity. Fluidity. Superposition. Superposition. Razor sharp. Razor sharp. Fragmentation dynamic stream. Fragmentation dynamic stream. Explore dynamism and movement. Explore dynamism and movement. Dynamism and fluidity. Dynamism and fluidity. Curvaceous fluid and sculptural. Curvaceous fluid and sculptural. Distort. Distort. Interpenetrating forms. Interpenetrating forms. Bold curves. Bold curves. Pushing boundaries. Pushing boundaries. Optimizing space. Optimizing space. Bachelor's degree in mathematics. Bachelor's degree in mathematics. Leisure center. Leisure center. Islamic calligraphy. Islamic calligraphy. Flowing arabesque. Flowing arabesque. Innovation. Innovation. Multi-viewpoint perspective. Multi-viewpoint perspective. Functionalism. Functionalism.
Appendix 1. What is parametric design? Parametric design is a method of design based on the use of parameters, which are variables that can be adjusted to change the design. By using parametric design, architects can explore a wide range of possibilities and iterate on their designs to arrive at the optimal solution. The term parametric comes from mathematics. It refers to parametric equations that use a number of parameters and variables. Parametric design differs from traditional design methods in that it is based on the use of parameters and algorithms. Traditional design methods rely on the designer's intuition and experience to create a design, often using trial and error and long hours modeling things manually to arrive at the final design. In contrast, parametric design uses a set of predefined rules and constraints to guide the design process, allowing for a higher level of precision, speed, and clarity. One of the main advantages of parametric design in architecture is its ability to generate multiple design options, allowing architects to explore a wide range of possibilities before settling on a final design. This is known as generative design, and it's a powerful tool for architects to have in their arsenal. Additionally, parametric design allows for precise descriptions of geometry, reducing errors and inconsistencies in the design process and making the construction process more efficient and cost-effective. Appendix 2. The benefits of parametric design.
For a long time, the architect's inventiveness was constrained by natural rules. Several artists have tried to go against the trend over the years, but it was never practicable on a wide scale. It just took a long time to transform an aesthetically appealing structure into an efficient structure. It took a lot of trial and error, time, and teamwork. Parametric architecture allows for creative freedom. It allows you to add a strong architectural signature to your creations by proposing complex shapes and providing an answer to various needs, sometimes subject to precise constraints. Modeling can be easily adapted to potential changes in the project. Finally, parametric architecture allows an optimization of the use of materials and thus grants a better control of costs.
Appendix 3. Future cities with parametric architecture.
Many experts are concerned that AI will progressively replace architects. Although that is a valid problem, an architect may be able to choose an alternative way. A team of architects may be required to develop entire cities rather than focusing on a specific project or neighborhood. With the advancement of technology, entire cities are becoming independent systems in their own right.
Appendix 4. Challenges and limitations of parametric design.
One of the main challenges of parametric design is that it can lead to a homogenization of architecture, with all buildings looking the same. This is because parametric design is based on a set of predefined rules and constraints, which can result in a limited number of design options. However, this issue can be addressed by giving architects more control over the design process and allowing them to incorporate their own design aesthetic and creative vision into the design. Another challenge of parametric design is that it can be seen as taking away from the creativity of the architect. However, this is not the case. While parametric design can automate some of the repetitive tasks of the design process, it still requires the creativity and expertise of the architect to guide the design and make decisions about the final design. A lack of understanding of parametric design can also be a challenge. Not all architects have the necessary knowledge and skills to use parametric design tools, which can result in a lack of adoption of this technology. A limited knowledge of parametric tools can lead to poor aesthetic results and has even given parametric design a bad reputation due to the parametric, but low-quality designs. However, with the increasing availability of online tutorials, workshops, and training programs, architects can easily learn how to use parametric design tools and take advantage of the benefits they offer.
Appendix 5. What's next for architecture?
The fears of AI taking over an entire industry are premature. However, there's no doubt that it is increasingly more common in architecture. It's up to the architects to embrace the new technologies and adapt to modern times. In a way, parametric technology allows them to focus on the things that matter. If they utilize all available tools, they will have a platform with which to further evolve. Whatever the future brings, it's going to be exciting to be a part of.